Hello, everyone. Good evening. Hello. Hello, can you hear me?
Yes, sir. Good evening, sir.
Good evening. Mary Ann, are you there? Miriam. Miriam Kabir, are you there? Saleh. Madaki. Sal, are you there? Okay, so let me share the slide so that we can start without wasting much time. So good evening, everyone, and welcome to CHM 102 Introductory Organic Chemistry Facilitation Week 4. This day, the 20th of March, 2023. So far, we have been discussing fundamental things that concerns organic chemistry and organic compounds. Last week, we ventured into nomenclature, and we looked at the various rules which you will arrive before we arrive at the IUPAC name of a particular organic compound. Today, very quickly, we are going to look at the nomenclature of aromatic compounds. You know, last week we didn't consider aromatic compounds. So very quickly, we are going to look at nomenclature of aromatic compounds, and then from there, we will move into alkanes. So please tighten your seatbelt, make sure you have good internet service, and always feel free to call my attention at any point as we continue.
Yes, sir.
Okay. Okay. Not too much.
It's too loud on the other side. Who is that person talking over there? Like I said, we are considering first and foremost nomenclature of aromatic compounds. We will conclude with that, then we'll now go to alkanes. So basically, we should have heard of benzene or benzene ring. And so this is what is called benzene ring. Okay. And then when you have two benzene rings fused together, you have a naphthalene. This is naphthalene. That is two benzene rings fused together in this form. Then when these two benzene rings are connected by a bond, you call it biphenyl. When the two benzene rings are connected by a bond, you call it biphenyl. It is called biphenyl because if we dissect this compound here, if we cut this compound here, we get two phenyl groups. And so it is called biphenyl. And then when we move, this here we have three benzene rings fused together, which is called phenanthrene. when this third benzene ring is angular, we call it phenanthrin. And then here we have another 3 benzene rings fused together. However, it's just unlike what we have in phenanthrin, where the third benzene ring is angular. In anthracene, the 3 benzene rings are linear. You can see the fusing. So we have benzene. This is the structure of benzene. We have naphthalene, 2 benzene rings fused together. We have biphenyl, 2 benzene rings fused together with a phenyl ring. And then we have the phenanthrin, which is 3 benzene rings. And then we have the anthracene, which is still 3 benzene ring in linear form, while phenanthrin is in an angular form. So benzene derivatives. You know, benzene itself is what we have here. This is benzene. So there are things you attach to benzene, and this will form benzene derivatives. So here, when benzene has 1 methyl group, it is called toluene. So, or methyl benzene. Both of them are recognized. IUPAC recognizes toluene, okay, because they were trivial names that have been used for quite a long time, and so IUPAC adopted it. So this is toluene, and then this is phenol or benzenol. When instead of CH3 you have OH, it is phenol. Of course, you remember when we were discussing functional groups, and I did mention that OH, where you have OH, the ending is always ol. Like in alcohol, the ending is ol. Now we are having a phenol, and then the ending is still ol. And then from there we move to benzaldehyde. Instead of having OH, if we have an aldehyde group, that gives us benzaldehyde. You can see the benz, then the aldehyde. Or rather, it is also called benzene carbaldehyde. Then, when instead of all those things, you have a carboxylic acid group, it is called benzoic acid. Benzoic acid. And then, when instead of all this, you have a NH2, which is a amino group, it is called aniline. It is called aniline or benzamine or benzamine. So the names on brackets are usually the normal IUPAC name. However, I've also said that even the trivial name or the common name of these aromatic compounds are also recognized by IUPAC. And then we have this one, when it's OCH3, that is a methoxy group. We now call it anisole, or methoxybenzene, So the benzene derivatives we have considered are toluene, phenol, benzaldehyde, benzoic acid, aniline, and anisole. Then we want to look at a substitution in benzene. So when you have more than one substituent, there is need for you to specify the position of the second substituent, because ordinarily a benzene ring is planar, and because it is planar, there is no difference between what we call 1, 2, 3, 4, 5, 6. Okay, what am I saying? If you come to this compound, this carbon here, 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 and this carbon here, they are equivalent. And so you cannot say there is a number 1, number 2, number 3. However, as soon as there is a substituent, like we have here in the benzene derivatives, you can see this is having a methyl group, this is having OH, this is having an aldehyde. So these carbons that have attachments are no longer the same with the other carbons that doesn't have attachments. And that is what removes planarity. And once planarity is removed, then there is need to specify the positions of other attachments. And that takes us to what we have here. Here you see we have this is a benzene ring, but we have 2 substituents, X and Y. And Y is ortho to X. just as X is author to Y. So whether it is X, that is the parent compound, is a function of what functional group is in X. Whether it is Y is also a function of what functional group is in Y. So however, this kind of arrangement is called author or the two position. Okay, so we'll see examples. Look at this example here. This is called author dichlorobenzene. Why is it called author dichlorobenzene? It is called author dichlorobenzene to show that the second chloro group is at the author position. Okay, to show that the second chloro group is at the author position. This chloro group, remember, it can be here, it can also be here. So when it is this way, you call it author, or you can say 2-dichlorobenzene. Then let us move away from author. We now have a meta. When it is separated by one carbon, that is called meta position, or otherwise called 3 position. So if you have a substituent here, if you have a substituent here and a substituent here, Y is meta to X, just as X is meta to Y. Okay, so what becomes the parent compound is a function of the functional group that is predominant, or rather the functional group that is given a preference. So we have a compound here. You can see the methyl group here. This dimethyl benzenes are usually called xylene. Dimethyl benzenes are usually called xylene. So you can see here we have orthoxylene, or 1,2-dimethyl benzene, showing that the two methyl groups are at 1,2 position, or this is author to this. Then we have a 1,3-dimethyl benzene, 1,3, showing that, or meta. You can see M here, which is the same thing as this meta here, showing that the second methyl group is at meta position. And then the third substituent we want to look is para position. I want to point out something, please. What am I pointing out? Just as this position is author, this position is also author to X. So these two positions are author to X. If we are considering Y, these two positions are author to Y. Then this is meta to this, just as this position is meta to both X and Y. However, the author position has just one position. Sorry, the para position is just one. Unlike the author and meta position that we have two positions, the para position is just one. And the para position is also called the 4 position. So if we look at the third isomer of xylene, you can see that the second methyl group is at para position, and so the name is paraxylene, or we can still call it 1,4-dimethyl benzene. Now you can see the one we have here between nitro and iodo. Okay, so you see is a para-iodo nitrobenzene. So we move on. Let us take a look again at polysubstituted benzenes. In polysubstituted benzenes, we give preference to the parent functional group, and then number the substituents, So we give preference or the parent name to the most preferred functional group, and then number the substituents. So that what we have here now, you can see, if we consider this as the methyl group, you can say this is 1, 2, 3. So there's another methyl group at 3 position, 4, 5. There's another methyl group at 5 position. So this compound will be called 1,3,5 trimethyl benzene. It is commonly known as mesitylene. So you can see the common name here, mesitylene. Now, if we move to this other compound where we have OH and Br, remember on our discussion in the nomenclature of alkanes. And we did say that when you have a OH, which is for an alcohol, and Br, which is for a halogen, that the OH is most preferred. And therefore, the parent name is going to contain the OH, while you number and name the halogens as a substituent. So if that is the case, then this compound ordinarily is a phenol. It is a phenol because you remember what we said. Look at this slide again. You can see this is called phenol. So let's go back. So you can see that is called phenol. And so this is either you go this way or you go this way. Let us see, both of them are supposed to give us the same numbering. So you must not go anti-clockwise. You can as well go clockwise. So this is 1, 2, 3, 4, 5, 6. And so you can see the bromo groups are at position 2, 4, and 6. And therefore, the name of that compound will be 2,4,6-tribromophenol. Then if we move to this point, okay, let me say we are numbering from this end. 1, 2, 3, 4, 5, 6. So you can see the substituents are still at 2, 4, 6 position. So it doesn't matter whether we are numbering from right or from left. Then we move to this compound. This compound is a very dangerous chemical. TNT is used as an explosive. Okay, trinitrotoluene is an explosive, and you can use it for quite a lot of things. So you can see this compound, the methyl group is the parent, so which means we have a toluene. Remember, this is a toluene. Okay, remember this is toluene, which means in this particular derivative, every other thing will now be called substituents. So we have nitro group at 2, another nitro group at 4, another nitro group at 6, and that is called 2,4,6 trinitrotoluene. The last one on this slide is there we have fluoro, and we also have a methoxy, and then we have a ethyl group. Remember what we said, that benzene with O-methyl, this compound is called anisole. This is anisole. So if you look at the substituent, the compound we have here, you can see this is going to be an anisole that has fluorine and also an ethyl group. Let us number also and see. This is a This is 2, 3, 4. So this compound will have a fluoro group at 2 position and a ethyl group at 4 position. The rule of alphabetical numbering comes into play, because here we have ethyl starting with E, and then we have fluoro or fluorine starting with F. So since alphabetically E comes before F, the name of this compound will be 4-ethyl 2-fluoroanisole. Any questions so far with what we have described in nomenclature of aromatic compounds? Any question? Any question? Okay, I'll take your silence for clear understanding, and then we move on. So let us now go on and look at alkanes. Alkanes are saturated aliphatic hydrocarbons with the general molecular formula of CnH2n+2 for acyclic alkanes. That is alkanes that are not in a ring form. However, for cycloalkanes, the general molecular formula will change from CnH2n plus 2 to CnH2n. So cycloalkanes will have CnH2n as the general molecular formula for cycloalkane, and then CnH2n plus 2 as the general molecular formula for acyclic alkane. Alkanes are also called paraffin. They are also called paraffin. So when you hear paraffin oil, you are talking of alkane oil. Under ordinary condition, alkanes are inert. What it means for a compound to be inert, it simply means that that compound is not reactive. So under normal condition, alkanes are not reactive towards whether it's an acid, because it is not basic, so it will not react with acid. It cannot even react with itself, so it cannot polymerize. Alkane cannot be oxidized, it cannot be reduced. Even halogenation, pyrolysis, aromatization, none of this happens so easily in alkane. None of them happen easily in alkane. And the reason is very simple. When we were discussing hybridization, you remember we agreed that in alkanes, there are sp3 hybrid orbitals. Alkanes are formed from sp3 hybrid orbitals. And in every alkane, you have only sigma bonds. And sigma bonds are formed from head-wise overlap. Okay, head-to-head overlap of atomic orbital. Okay, they are formed from head-to-head overlap, and so sigma bonds are the strongest. Okay, they are stronger than pi bond, and because sigma bond is what is found in alkanes, alkanes are naturally unreactive. However, they can still undergo one or two reactions using free radical mechanisms. Sources of alkanes. The sources of alkanes include petroleum, natural gas, coal, carbohydrates, fats, and oil. All of this contains alkanes in good quantity. Okay. So let us continue as we look into the compounds. Let us now, we have mentioned that the sources of alkanes are petroleum or crude oil, natural gas, coal, carbohydrates, fats, and oil. But the major source of alkane is crude oil or petroleum. That's the major source of alkane. So for us to discuss extensively the source of alkane, it means, in other words, to discuss how crude oil are composed of alkane. So let us go on. Composition of crude oil. Crude oil contains alkanes up to 40 carbons. Alkanes of up to 40 carbons are contained in crude oil. They contain cycloalkanes. They also contain naphthalene and other aromatic compounds. You can see the chart here. The chart here showing the composition of crude oil. It has 83 to 87% carbon, 10 to 14% hydrogen, and then little nitrogen, oxygen, sulfur, and less than 0.1% metals. So our interest is carbon and hydrogen. So you can see that the greater percentage of crude oil contains alkanes. The other component or the other source of alkane we want to consider is natural gas. Natural gas contains 80% methane. And you know, methane is the simplest alkane you can think of, or rather even the simplest organic compound is methane. Okay, so natural gas contains 80% of methane, 10% of ethane, and then the remaining 10% is mixtures of higher hydrocarbons. So you can see how these two sources are the key source of alkane. You can see how they are the key source of alkane. Now, in crude oil, even from the name crude, you can see it is not refined. You can see the compound is still not useful because it contains quite a lot of things. As a matter of fact, crude oil is a composition, is a mixture of hydrocarbons. It contains quite a lot of hydrocarbons. So for us to be able to use our crude oil, or for us to be able to assess the alkane component of crude oil, then we must refine the crude oil. Okay, and what is called refining is simply fractionation of petroleum. Fractionation here means, remember we said it's a mixture. So using temperature, okay, to separate these mixtures into various components or compositions depending on their boiling point. Okay, so, and that is why the simplest way to start describing refining is to look at fractional distillation. That is the first step, okay, in refining, fractional distillation. And what happens in distillation naturally? In distillation, you heat the components, okay, vaporize, okay, the component which is volatile will now vaporize, and then it will condense at a point, and then this condensed component is collected as a condensate or distillate. So in petroleum refining, when you heat your crude oil to about 650 Kelvin, you are going to generate hot liquids. And this hot liquid passes through a flash chamber. And in this flash chamber, low boiling fractions, of course, are volatilized. They are converted to vapor first. Of course, vaporization and or volatilization starts with low boiling fractions. Okay, so the low boiling fractions will boil first and get vaporized by lowering the pressure. Okay, and then as it forms vapor, this vapor passes through a tall bubble tower filled with horizontal stainless steel tray. And then each of these tray provides with is provided with a chimney covered with a loose cap called bell cap. Okay, so as the vapors ascend, they become gradually cooler. As the vapor is going up, they become gradually cooler, and therefore various fractions condense at different heights. The lowest boiling will be collected at the top, while as the boiling point increases, the collection point decreases. So when you look at let's look at a column, a fractionating column. Okay, this is a typical fractionating column that we are describing. You can see this is our crude oil, and this crude oil passes through this chamber, and what happens in this chamber is heat. You can see furnace. Once you see furnace, we are talking of heating. So when this crude oil is heated with a furnace, this crude oil vaporizes. Okay, the crude oil, first of all, will be converted to hot liquids, and this hot liquid will be converted to vapor, and this vapor enters this chamber. Okay, you can see the movement upwards. The lower boiling components will be the one, of course, you can see volatile gases here. Okay, that is the lowest boiling component. And then after the volatile gases, you see gasoline, or what we call premium motor spirits, or what normal person call fuel. Okay, then after this point, you now have the kerosene. Okay, and then after this point, you have the diesel oil. After the diesel oil, you have the lubricating oil, and then after the lubricating oil, you have the residue. Now, if you go down, you will see that the boiling point is increasing. The volatile gases have the lowest boiling point, followed by the gasoline, followed by the kerosene, the diesel oil, and then the lubricating oil. So this is a typical bell curve, which we already described. You can see the position of the bell curve here. So quickly, we are going to be looking at the boiling point, components, and then the approximate composition. What are their uses? So natural gas at 293 to 373. When you heat your crude oil at 293 to 373 Kelvin, you are having approximately carbon 1 to carbon 4. And carbon 1 to carbon 4 are naturally gases. Okay? Methane to butane are naturally gases. And then these are used in refinery and also for domestic fuel. Then after your natural gas, we get the light petrol. The light petrol boils around 343 to 363 Kelvin. Okay? And that is C5 to C7. They are majorly organic solvents. Then we now have the benzene, which boils around 353 to 393. And they contain C6 to C7. And these are used as dry cleaning, okay? Maybe to clean surfaces. Then we have the ligroin, which boils from 343 to 473, okay? And components of these are C6 to C8, usually used as solvents. And then the gasoline or premium spirit. The premium is above 573 Kelvin, not degrees C. And these are composed of C6 to C11. They are used as motor fuel. We have the kerosene, what is also known as paraffin oil. And these boils above 573, and they are composed of C12 to C16 that are used in lightning. Then we have the lubricating oil. We have the gas greases, the Vaseline, petroleum. We also have the paraffin one and the residue. You can see there are various boiling points. Synthetic petroleum. Why did they not obtain synthetic petroleum or synthetic fuel? And the synthetic fuel in two major. Number one is a process. In process, the source, okay, so finely powdered hydrogenated such as tin and lead to give a mixture of liquid hydrocarbons. As you see here, powdered coal, and this is the paste. You have powdered coal, you have, therefore, we are going to, this paste form hydrogenated. You can see hydrogen here entering the tower. And that hydrogen is carrying out hydrogenation. And after hydrogenation, liquid comes to this chamber where it is converted to gas. And this gas comes to this chamber where it is condensed. And then this condensed gas is what is called crude oil. So you can see from coal, one can still generate crude oil simply by passing the coal through heavy oil and through passing it through hydrogen. And this hydrogen will be converted to gases, and these gases will be condensed. This will be fractionated, just like we have discussed earlier. It will be fractionated to gasoline, kerosene, oil, and the rest. The next aspect of synthetic fuel is Fischer-Tropsch process. In this process, water gas, which is a of carbon monoxide, mixture and hydrogen is called water gas. So water gas is obtained by the reaction of steam with red hot coke, that is red hot carbon. So the water gas is mixed with half its volume of hydrogen. So you hydrogenate the water gas, and the catalyst used in the process is a mixture of cobalt, thoria, magnesia, and keselga. Of them in 100. So with these three catalysts, the hydrogenated water gas, okay, yields crude oil. The hydrogenated water gas yields crude oil. This is a typical chamber for the convert water gas to crude oil. You can see this is our water gas. Remember, this water gas is generated from coke. Okay, so this water gas is hydrogenated. You can see the point of entry of hydrogen is hydrogenated and then comes to this chamber. And in that chamber, the water gas is acted on with ferric. And then this ferric oxide is carrying out purification of the gas. Okay, then also we also have the carbonates and ferric. This continues the purification process, and then as soon as it is purified, the gas comes to a compressor. What does a compressor do? A compressor helps in converting the gas to liquid. Okay, cobalt, thoria, and magnesium. This is magnesia or magnesium 2 oxide that will act on the compressed natural gas here, water gas, and then this is cooled here. Okay, as it's cooled, it condenses, and then the condensate comes to the fractionating column where gasoline and the rest of the mixtures will be separated. Octane number. We must have heard of octane number right from our secondary school, which is a measure of how a crude oil, or rather a petrol, burns. Okay, it is a measure of how a petrol burns. Okay, so octane number was obtained because 2,2,4-trimethyl-pentane, which is also called isooctane, was considered a good fuel. Okay, just by using it, 2,2,4-trimethyl-pentane or isooctane was considered to be a good fuel. and therefore it was given the octane number of 100. However, N-heptane, well, and then N-heptane was given of 0. So 2,2,4-trimethyl-pentane is 100, N-heptane is 0. So if we have equal mixture of 2 isooctane and N-heptane, if we have equal mixture of isooctane and N-heptane, we expect that the octane rating of this equal mixture will be 50. 50 because we are mixing 100 with 0 and dividing by 2. So when you mix 100 with 0 and divide to 100 and divide by 2, you get 50. So octane number is the percentage of 2,2,4 trimethylpentane and N-heptane. So you want to find out the percentage of 2,2,4 trimethylpentane present in the mixture, okay? In the mixture, and then which has similar ignition properties as the fuel under examination. Of this has an octane rating of 50. 1:1 mixture has octane rating of 50, and then commercial gasoline has octane number ranging from 81, 74. In short, anything above 50 is considered a little good, but the best, the premium, when you say this is premium motor spirits, then it must have octane number of at least 81. So you can see 81, 75, and 65 represents premium, regular, and third class or third grade gasoline. So good quality motor fuel must have octane number of 87 to 95%. And that is to show that it's going to be so closer to 2,2,4-trimethylpentane. These octane numbers are affected by some factors, which includes the chain length, okay, branching. If you have a straight chain alkane and a branch chain alkane, both of them have the same carbon number. The branch chain alkane will have better octane rating because branching increases also as the chain length increases. And that is to say that if you have two compound you want to assess for octane number, if one is, say for instance, butane and the other one is a pentane, butane will have better octane number than pentane. So as the number of carbon increases, the octane number decreases. As the number of carbon increases, the octane number decreases. Unsaturated hydrocarbons have higher octane number than saturated. Cycloalkanes have higher octane number than the corresponding acyclic alkane. Take note that we are comparing cycloalkanes to straight chain alkane, not branch chain, because branching naturally decreases octane, increases octane number. Octane number boosters. Because octane number is very important, because it is necessary that a good petrol should have good octane number when there are some compounds that could be added to your alkanes to improve the octane number. These compounds are called the octane number boosters. They are also called anti-knock. Because when the octane number is not good, the compound, using that compound for gas for engine, predisposes the engine to knocking. The engine can knock. So these compounds that are added boost the octane number, and they are also called anti-knock. A very popular one is triethyl lead. However, Triethyl lead is discouraged because of the environmental pollution. It introduces lead to the environment, and lead is a poisonous chemical. The other anti-knock is a tertiary butyl methyl ether. It is a good anti-knock. So any one of these, when added, improves the octane number. Aside octane number, we also have what is called cetane number. If you remember last week, when we were looking at a nomenclature, we mentioned something about cetane. Cetane is a 16 carbon alkane. You can see the structure here. This is the structure of cetane. If you count it, you see there are 16. So in diesel engines, fuel having low octane number are much more useful than those having a higher octane number. So octane number is only good for petrol engines. Good octane number is not good for diesel engines. So diesel engines want bad octane number, just as fuel engines want good octane number. So in other words, the straight chain hydrocarbons constitute a superior fuel than the branch chain hydrocarbons in diesel. So diesel will prefer straight chain hydrocarbon than a branch chain hydrocarbon. So quality of diesel fuel is expressed in terms of the number called cetane number. Cetane, I have said, is 16 carbon compound. So when there is equal mixture, cetane itself, being a good diesel fuel, is rated 100, whereas alpha methyl naphthalene, a very poor diesel fuel, is rated 0. So if you have equal mixture of cetane and alpha methyl naphthalene, if you have the equal mixture, you are going to have a cetane number of 50. And then you use this cetane number to assess your diesel to see whether they meet the requirements. Difference between octane and the cetane number, very simple. Octane number is a measure of the performance of a fuel, while cetane number is a measure of the delay. How can this fuel be delayed to ignition? So when it is well delayed to ignition, it has good cetane number. When it is not delayed at all, when it can burn, combust immediately, it has good octane number. So octane number is important for predicting the knocking of an engine, while cetane number is important for predicting the ignition of an engine. Then octane number is given for gasoline, while cetane number is given for diesel. Octane rating is done considering the octane number of isooctane, while cetane rating is done considering the ignition of cetane. Question and answer. So now is the time for question. Now is the time for question. Time for question. Miriam, are you still there? Miriam, do you have a question?
No, sir.
No question.
Yes.
You understood everything?
Yes.
Did you receive my mail today?
No.
I sent a mail this around after 3, reminding people about this class and then also sending the PowerPoint. Did you get it?
No, no, sir.
Have you checked your mail recently?
Yes.
Like from 3 p.m. you have checked your mail?
Yes, I'm even checking it now. There is no mail.
So your student email that is on the course page, is it not going?
Is going.
So have you ever received mail from me?
Yes. Last week.
Okay. Okay,
Is
you
it
received
last
mail
week?
last week.
Yes.
Okay, it's okay. Mikolin, are you there?
Yes, yes, sir.
Any question?
Well, my question is, I just joined recently, so
Speak up, or you use the chat. I can barely hear you.
okay, can you hear me now, sir?
Yes.
Okay, I just joined recently, so I didn't quite get the topic of this section. This one.
Okay, this section we are looking at the. First of all, we had an unfinished business last week, which was a nomenclature. We didn't conclude the nomenclature of aromatic compounds. So that is what we completed. And then we started with alkanes.
Okay, sir.
So we are on alkanes now. We are not yet done with alkanes. We are continuing next week.
Okay, sir.
Okay, Nana, are you there? Hello, Nana.
Yes, sir.
Nana, your network is not stable.
Okay, good evening, sir.
Good evening. Any question?
No, sir. I
You
understood
understood everything, or you came
sir.
late?
Yeah, I actually came late.
Nana. Stop now, stop coming late so that you will follow everything and have questions to ask if need be. Meanwhile, I will advise that you can get the full this thing from the course page. Once you go to the course page, there is down, you get the facilitation, and there you can get a video, sorry, a link to each of the facilitation we have done, in case you missed any. With that link, you will be able to also follow and have your question well written for next week. I want you to ask a question next week.
Thank you, sir.
All right. Hello, Grace.
Yes, sir. I'm hearing you, sir. Good evening, sir.
Any question?
Actually, sir, I entered late. Couldn't
Please.
capture anything, but I hope if I go through the recording, I feel pick something there.
Okay, please make sure that you go to the course page, access this as and then access this live session so that you follow everything we have discussed. And then also maybe next week, please try and come a little earlier so that you can ask questions, please.
Okay, sir.
All right. Okay, we don't have, the other people have left. One thing I want to find out from you guys is this. From the course page, I'm expecting up to 800 students here.
Yes, sir.
Why is it that only few attend?
Maybe there are times that some did not have data, or maybe they are busy, and maybe some didn't get.
Busy with something, right?
Yes, sir. Or most of them they didn't get the information now about the class.
The email I send usually, I'll just go to the course page. The email I send.
Okay. Well, actually, I didn't even get any email.
Everybody.
I actually didn't get any mail. I just saw this link on the WhatsApp group. Maybe it was sent by Isha, I don't know. So I just clicked on it.
The email address you have on the course page, is it going?
Yes, sir.
You have not received any email for Chem 102?
No, I don't think so, but I will check now.
Please check, because it's a serious problem if you are not getting mail and you have email there. All right, so see you next week. While we wait for next week, I would want you to go through alkanes. That will be the topic we are going to continue with. Today, we have been able to look at what alkanes are. We have also been able to look at their sources and how you can get alkane from crude oil and how they can be used in gasoline and other engines. Please, I want you to, using the course material, I hope everybody have the course material.
Yes, sir.
Sir.
Yeah.
Yes.
Oh, yeah.
Okay.
Sorry, excuse me, sir.
Yes.
I have not been getting
You have not been getting email from me. Hello? Please, can you use the chat? Use the chat in case your network is bad. You can chat. Just drop a question.
I don't know.
there.
Why? Yes, sir. Okay, sir.
I've not been getting any at all. I just checked now. Oh. Hello, is anyone there?
Please use the chat.
Okay, sir.
I'll send a mail today. If anybody didn't get the mail, the person should. Okay, somebody said he has been getting the email. I haven't been getting. I have not been. Okay, it's okay. It's okay. So, do you know what will happen? I'm dropping my email address right here so that in case you have another email that is going, you just quickly send me a mail after this class so that if I send from that of a course page, I can as well send you a personal email. Please, I'm dropping my email address immediately. Even though one of my email address is on the first page of this PowerPoint. So one can as well get my email address from there. Please, for all these people that are just joining for today, I want you to go and visit the course page. In the course page, you are going to see, wait, everyone, please. Go and visit the course page. On the course page, you are going to see facilitation. And under that, there will be a place called recording. When you go to that recording, you will see link and password or passcode. Click the link, enter the passcode. You will be able to access all the facilitations from week 1. From week 1 to the last week, you will be able to access all the facilitation. And once we are done, and there is still time, we will fix at least 1 week. So that, I mean, one hour facilitation where we are going to treat only questions and contributions. So that those who missed our earlier classes will now be able to join, okay, haven't gone through those live sessions from the course page. You will now be able to ask questions. I hope what I said is clear.
Yes, sir.
Okay.
Thank
So
you.
see you
Thank
next
sir.
week. Huh?
Thank you, sir.
Okay, I thought you wanted to say something, Grace.
No, sir. No, sir. I've sent my email. Yes, sir.
Okay, okay. All right, see you next week, please.
Yes, sir.
Come on. How did it?